All right. And we're live. So we've gone through probability with normal distribution, z-scores, and hypothesis testing through this week. So I'm going to go back and we'll cover linear regression again. I am going to add something new this time that we didn't really have a chance to cover last time. So after we go through our linear regression t-test, we'll take a look at residuals as well. So as fast as I can, what we're doing with linear regression is we're trying to get an estimate for a best fitting curve. But we're going to do that by looking at the correlation coefficients, as well as this strength, linearity, and slope of the correlation. So a correlation is a measurement of how strong two variables are related. A strong correlation just means that one variable can be used to predict the other. If your correlation is positive, then in general, as one variable increases, the other variable increases. These are all positive correlations that I'm showing here for these two, where these, this one's also a positive correlation. But these two here in green are negative correlations, because in general the trend is downward. As far as the strength of the correlation goes, if you've got anywhere from 0.6 or above, then that correlation is strong. If you've got a relationship between 0.4 and 0.6, we could say that the relationship is moderate. And then anything below 0.4, we could say the relationship is weak. It's important that we don't take correlation to mean that a cause-effect relationship. Just because a relationship exists doesn't mean that that relationship is a cause-effect relationship. Our textbook example is the relationship between murder and ice cream sales, where the murder rate and the ice cream sales tend to relate together. So as one increases, the other increases, but it doesn't mean that murders cause ice cream sales or that ice cream sales cause murders. It's probably a third outside variable that's affecting both of them. Ice cream sales tend to be higher in the summertime when it's hot outside. When it's hot outside, people tend to be angrier. There tends to be more contact between people versus the wintertime when people tend to stay at home. So it's probable that there's a third outside variable, possibly heat or season, that affects both of these. So just because two things are related doesn't mean it's a cause-effect relationship. So to get a best fitting line, what we'll be doing is we'll be taking a look at every value that we have observed in real life. So here in blue, I've got our observational data, and trying to get a best fitting line, so the line that comes closest to all of our blue dots as possible. So all of these red dots are our predictions based on our observations. Okay, so we talked about a process of getting our least squared regression lines. That means the line that has the lowest residuals. Our residuals are our error, which is our new part for today. Our error can be found by subtracting the observed value minus the predicted value. So in this case, I've got a negative residual for the point at y3, because my third point here is below the predicted line. Okay, so we had a long method last time of getting our slope that we went through. And then we used that slope and one average point for x and y to create a least squared regression line, which we could also use in order to get, looking at our sample standard deviations of y and x, our correlation coefficient. Thankfully, you guys don't have to do this by hand because we have calculators. So although we did do this once by hand in quarter 3, I'm not going to do it again by hand since all of your final exam questions are going to expect you to have a calculator instead. So I'm going to focus on getting a least squared regression line using a calculator. In order to do it, you would hit stat edit and then create two lists of values. And then conduct a linear regression t-test to get your best fitting line and your p-values. That's your probability that this best fitting line slope could be the actual best fitting line slope if there was a zero correlation. So if there was no correlation, what's the probability of randomly getting a slope that is this big? Okay, so I'm going to run through an example really quick. Okay, so here I've got a bunch of planets. Which I realize this is old and Pluto's not technically a planet anymore, but I've got a bunch of planets with their distance of the semi-major axis of their orbit. So if this is the Sun, and this is our planet, I'm getting their distance at the point where they are furthest away. Okay, so I've got their distance and I've got their periods, which is the time it takes to complete one rotation around the Sun. So for Earth, it takes us 365 and about a quarter of a day to rotate around the Sun once, which is why we have a leap year. Every 4 years, we have an extra day to make up for that 0.26 of a day. Okay, any questions on what our table represents? Okay. So what I'm going to do is I'm going to see if I can find a relationship between the distance and the period. So I'm going to call this x and y, my input and output, between these two variables. Okay, so the first step would be here in our calculator. Clear everything out. First I'm going to go second catalog. And then down in D, I'm going to turn diagnostic on. So that allows us to get information about our correlation coefficients. But that does mean that our calculator is going to take longer to produce best fitting lines. Okay, once I've done that, I'm going to hit stat, edit, and we're going to type in our lists. So I've already done this beforehand just to save us some time. So list 1 is our distances in million kilometers. Of each planet's largest distance from the Sun. And then list 2 right now is our periods. Okay, second quit. I'm going to try to store this extra data I have for another problem really quick. Store as list. Okay, none of that's necessary. I'm just saving some stuff for an example coming up. So I'm going to clear out list 3 and list 4 since we don't need them right now. Okay, so you should have 2 lists, one for your input and one for your output when you do this in your calculator. Okay, then I'm going to hit second quit, and we'll go with stats, calculate, and I'm going to do linear, quadratic, cubic, logarithmic, exponential, and power, and record their r-squareds. So here's a linear regression if you don't type any inputs or outputs. So it'll automatically do list 1 as your input and list 2 as your output, which is what we've got, so we're okay. So linear's r-squared was 0.978. So this is 0.978. I'm also going to test quadratic, cubic, logarithmic, exponential, and power. Oops. Okay, so exponential. Oops, quadratic next, sorry. Quadratic has an r squared of 0.9997. Okay, cubic. Uh, 0.99997. So far cubic is our best. Okay. Linear, or sorry, logarithmic. Logarithmic 6.7, which is too low. Exponential. Okay, I'm looking for my highest r squared right now. It's the highest strength of the correlation to the data. Exponential 0.78 something, which is too low, and then power. Okay, so that is the strongest correlation to the data. I've got 1, 2, 3, 4, 5, 6, 7 nines before we got to a 7. So my strongest correlation to the data is a power function. Okay, and if I take a look at this, this says my y value is some constant a, I'm not going to worry about what that represents in real life just yet, times my input, which is my distance, raised to the 1.5 power. So I've got my period, y, is equal to some constant a times x raised to the 1.5 power. Okay, that's my y is period, so this is the period, is equal to some constant a times our distance to the sun raised to the 3/2 power. If you remember, 3/2 is the same thing as raising something to the 3rd power and placing it underneath the square root. So I'm going to square both sides, and this will become our period squared is equal to some constant squared times our distance cubed, which means our period squared is directly proportional to our distance cubed from the sun, which is, if you guys have taken physics, Kepler's 3rd law of planetary motion. Normally written like this. Your period squared is directly proportional to your orbital radii cubed. Okay, we can do a little bit better than that, get a little bit more information for that. If I untransform this power function, so I'm going to start calling on people since this is all review anyways. Andrew, if our best fitting function is a power function, how can I undo that power function to do a linear regression t-test? Yep, do I need to take a natural log of x, natural log of y, or natural log of both to undo a power function? To repeat, in order to transform a power function back to a linear function, do I need to take the natural log of x, the natural log of y, or the natural log of both? Natural log of both, perfect. I'm going to make a table for that really quick. So this is type and how to transform to a linear function. Okay, so if you already have a linear, you don't need to do anything. If you have a logarithmic function, Then you can take the natural log of x. If you have an exponential function, you would take the natural log of y. And if you have a power function, you would take the natural log of both. Okay, I'll prove one of those really quick. So if I calculate our exponential function here, we get our equation. Y equals ab raised to the x. If I take the natural log of both sides, ln y is equal to mx plus b, and then solve for y. So I've replaced y equals mx plus b with ln y instead. Then my new y would be e raised to the mx plus b, which is e raised to the b power times e to the mx, or some constant c e to the mx, which is a constant, times a variable raised to the x power. Okay, so what I'm going to do is I'm going to untransform this power function by taking the natural log of x and y, and then we'll be able to do a linear regression t-test with it because it will be a line shape. Okay, I'll show you what it looks like graphically after I finish too. So this is for list 3, I'm going to take the natural log of our x value, which is list 1. For list 4, I'm going to take the natural log of our y value, which is list 2. Okay, now it is possible if you have any values that are 0 or negative that your calculator will throw an error here. And that's because you can't take a natural log of 0 or a negative number. If that happens, you'll need to transform this by adding enough numbers to make sure that all the values are positive. That does change what your y value or x value represents. Instead of just representing distance, if I had any negative distances, isn't really possible, but if you did have any negative distances and you added 50 to make them all positive, then your new x value would be distance plus 50. Okay, so let me just graph what we did. So I'm going to turn a stat plot on for list 1 and list 2. And we'll set our window so that we can see that. So I'm going to hit zoom and go over to zoom stat. So you can see here's our general curve of my x value right now is the distance away from the sun, and my y value is the period. So you can see we've got this power curve here. As we are further away from the sun, our period, the time it takes to revolve once around the sun, is increasing. Okay, but it's not a line yet. So if I want to convert this to a line, we can take the natural log of both x and y, and if we do, we will get a new set of scatter plots that would look like our list 3, the natural log of x, and list 4, the natural log of y, which if I zoom stat now looks like almost a perfect line. Okay, that allows us to take a linear regression t-test of list 3 versus list 4. So this is really a linear regression t-test. I'm looking at y equals mx plus b, but instead of y, this predicted value for y is really the natural log of our original y. And our predicted value for x is really the natural log of our original x. So this is really the natural log of y is equal to m times the natural log of our original x plus b. But we're graphing it as a line. That way we can still get our correlation coefficient to our data and get a p-value. So how probable is it that this natural log of y equals m natural log x plus b would have an m that is this big or small if the real m was 0? So if there was really no correlation, what's the probability that we would randomly get results that give us a slope of this large or this small with our data? So to give us an idea of whether or not this is due to random chance or whether this is an actual relationship between two variables. This is what we're trying to prove. Okay, so if we calculate, I've got, holy cow, we have a ridiculously small and astronomically small p-value. Okay, so what this means, this t-value here, is how many standard deviations you are away from the median. So if we had a bell curve where our mean was a slope of 0, in order to get a random value that is as far to the right as our value that we got for the slope, you would have to be more than 7,000 standard deviations away from the mean. Holy cow. That's not actually a factorial. That was just me trying to emphasize how big this is. But 7,000 standard deviations is ridiculously large. You can see that leaves us with a p-value of 1.5 times 10 to the negative 28th. That means we could be 1 minus p confident in our result. That would be 99.26 more nines after the decimal place % confident that there is a relationship between distance and period, or that our period squared is directly proportional to our distance cubed. That was a lot at once. Any questions on what we did so far? Okay, so I'm going to show us our results a couple more times and just ask some questions about it. So Abby, starting with you. What is the correlation between x and y? Is the correlation positive or negative? Okay, we have a positive relationship. Is it a strong, moderate, or weak relationship? Strong. And what model is it? Can't see. This is actually behind the calculator for our best fit. Power. Okay, so I have a strong positive relationship to a power function. Okay. There is a strong positive relationship to a power function. A little busy here as far as stuff going on screen, so I'm going to erase some of this. Okay, we used a power model. The equation for that model was here. Okay, I'm going to hit second, calculate a power regression again so I can get our power relationship back on screen. So y equals a times x raised to the b power. Where a is 0.1994 and b is 1.500. Okay, the r squared that we got was 0.9999. I could keep going, but that's enough. Okay, Eric, what does our r squared tell us about the planets and their periods? Okay. because the power model had the highest r squared. There is a power relationship between planetary distance to the sun and orbital period, which we were able to prove exactly what type of power relationship by undoing it. Since we had something raised to the 1.5 power in our power function, here's x raised to the 1.5 power, that's our distance raised to the 1.5 power. It's the same thing as the distance raised to the 3/2 power, which is the square root of the distance cubed. If I square both sides, that's period squared relates to our distance cubed, is what we were able to prove. Okay. Yes. Nikita? My screen is black. I am showing that I'm projecting, so let me just stop sharing screen on Skype and we'll try it again. Okay, let me know if it comes back up. I'm going to jump to Kyle. Kyle, if I get our linear regression t-test back up. Okay. Kyle, what was our p-value? No, the p-value is not the standard deviation. We need the standard deviation to get the p-value, but they're two different things. First, what's the number for the p-value? Close. 1.5 times what? What does this e to the negative 28 mean? This is scientific, there you go, times 10 to the power of negative 28 is our p-value. Okay, so what our p-value means is this is the probability that we could randomly get a result that is this far away from zero, from a slope of zero. So this is the probability that if there was no correlation between planetary distance and orbital period, we could get results with this type of distribution. You can see the probability is super low. If there was no correlation between orbital period and distance to the sun, the probability of randomly getting this result would be 1.5 times 10 to the negative 28th power. I'll write really quick. If there was no correlation between x and y, so that's our distance to the sun and orbital period for us, the probability of randomly getting results like ours would be 1.5 times 10 to the negative 28th power, which is super, super low. There's almost no chance of this happening randomly. Okay, does everyone understand what the p-value means? I think this was the most missed part of the test last time. Going once, any questions on p-value? twice sold. Okay, so that's it for our people over on Zoom. So that brings us to our Skype list. On Skype, I've got Nikita and Niall. So starting with Niall, we have a dwarf planet, Eris, which has a distance from the sun of 14,410 million kilometers. If our model was okay for something that large, how could I get the expected orbital period? Okay, now can you hear me? Okay, I think we've lost Niall. I'm going to jump over to Nikita. Nikita, same question. So if Eris has this distance of 14,410 million kilometers, and that was okay for our model, then what would I do to figure out the period of Eris? Right now, our distance is x. So that's distance from the sun in million kilometers. And y is our period in days. Okay, so if we know the distance from the sun of this particular dwarf planet is 14,410 million kilometers, how could we use this information that we got from our correlation, our nonlinear regression t-test, to figure out what the orbital period of this planet would be?
You mean orbital period, how long it takes for the planet to circle the sun, right?
Yes.
Okay. So wait, do we know the speed of the planet? I can see the info.
We don't. This isn't actually a physics question. This is a pure math question. So we came up with our power regression formula that we said has a super strong correlation to the data, right?
Yes.
Okay, so using this formula, how could you figure out what the orbital period would be in days?
Is it just AX times B, so 0.1 0.199 times 14,410 and to the power of 1.5?
That's perfect. Okay, so what we're going to do is we're going to take this equation and we're just going to plug in 14,410 kilometers. So in your calculator, whatever your last regression test did is stored in your calculator automatically. So I'm going to hit y equals and then hit variables, statistics, equation, regression equation. And that will paste in the last problem that we did. So here's our power function that we found. Then I'll hit second quit, and then to plug a value into that, I can hit variables, y variables function y1, and just plug in what we want, which is 14,410. Should give us our output. So it would take Aries 345,645.5 days to orbit around the sun once, if our model was okay for that distance. 345,645.5 days. Okay, however, our model is not okay to work for Aries. So last question, I'm back to Andrew. Looking at our original data that we used to build this correlation and the new data for Aries, Aries has a distance of 14,140 million kilometers from the sun. Why is it not okay to use our power regression model for Aries? Not that the y will be too large. We built this relationship with distances between 57.9 million kilometers from the sun and 5,900 million kilometers from the sun. Is Aries within that range or outside that range? Outside that range. Okay, so we do have enough evidence to say that this relationship holds true with our original distances. So that's 57.9 million kilometers to 5,900 million kilometers. We don't have any evidence to say that this relationship still exists outside this range. So if you're closer than Mercury or further away than Pluto, we don't know that this relationship is still true. So it's not okay to use this model for Aries from a pure mathematical perspective. So I could say Aries' distance is outside the range used to construct our power regression model. And therefore, we don't have any evidence to suggest that the relationship between distance from the sun and orbital period still exists. Now, some of you in physics might be questioning this right now, since what we just proved mathematically was Kepler's law from observational data, and you guys know in your physics class that this law still holds true no matter how far away we go from the sun. However, what we're looking at right now is pure observational data, and we're trying to predict that observational data based on our results. And if you do go far enough away from the sun, the pull of other larger bodies is going to change this relationship so that we don't quite follow this pattern. If you were going to go really close to Andromeda, for instance, so the closest star system to us, then Andromeda's pull is going to be what's capturing objects into its gravitational orbit rather than our sun. So the impact of Andromeda is going to be more present than the impact of our star. And this relationship won't hold true for distance from our sun. Okay, any questions about what we did? So anything from this problem? Okay, the last thing I want to talk about is residuals again. So we saw this at the very beginning of quarter 3, and then I never talked about it again. But residuals means error. The residuals is the expected value, the difference between the expected value and the observational value. Make sure I've got the order right. This is observed minus expected. So observed minus expected. Give myself more space. So the observed value is what happened in real life, and the expected value is what our model predicts will happen. So your residuals, or your error, is what what actually happened minus what our model predicted to happen. If you end up with a pattern to your residuals, then you know that the model that we chose is not the best possible model. So if I do this, I'm going to zoom out a bit. I've got several different models: linear, logarithmic, and it's a different type of logarithmic, but looking at these, hold on. Linear, this is exponential actually, and this one's logarithmic. Okay, so I've got linear, exponential, and logarithmic models of our price versus miles here, data for a certain make and model of car. So how many miles have you driven the car, and then what's the value of the car? You can see that there is a pattern to the residuals. In general, my residuals are curving this way. So that tells me that model 1 is not going to be the best model for our data. I still kind of have that pattern for model 2, our exponential model, where there is a set pattern for our residuals. So that tells me there might be a better model here. Here I don't have a set pattern for curves. I go down and then up and down and up. So there isn't a clearly defined curved pattern. So that tells me that this should be a better model than the other two. So this is an alternative to just looking at the r-squareds and looking at what's the highest r-squared. If I just gave you data for the error of each model, you could still figure out which one is the best fit to the data, even without knowing r/r-squared, by looking at the residuals and telling me if there's a set pattern. Okay. If there is a pattern to the residuals, so that means either everything curves in a line, or you've got a definite line for your residuals, or all of your residuals are above the curve, or all of your residuals are below the curve. If there's any of those patterns to the residuals, then a better fitting model exists. All right, and that's the only thing new for today, really, is for the homework, you're going to have a couple residual graphs that you'll need to interpret as well. And all you'll be doing is looking for a set pattern. Okay, any questions on anything from today? No. All right, I'm going to close with just a fun example for how I'm using this in my own free time. So I am currently playing a video game called Star Wars: The Old Republic. And in it, you can wear different armor sets that give you stats. One of those stats is called endurance. And based on your endurance, your health increases. So what I did was I created a quick table of what my endurance was with a bunch of different armor pieces and what my maximum health was within my video game. And I was going to try to reverse engineer what the curve was so that I can make predictions. If I have a set number of endurance, what would my max health be? And I can use this to try and figure out whether it's worth my time or not to try and work towards a new piece of gear. So this would work in almost any video game that has armor or clothing materials that you can swap in and out to change your stats, change your statistics. So if I do this, I've currently got a list 5 and list 6, which is my endurance and max health. And after playing around with this a bit, I was able to calculate that a cubic regression had a really good fit to that data, list 3 and list 4. Okay, so you can see I have a really high R squared to my data. Oops, that was the wrong one, wasn't it? Not list 3 and 4. I've got this stored as list 5 and 6 now. I had to move it because we used list 3 and 4. My bad. List 5 and list 6. Okay, I've got a super high R squared to our data. So that tells me I could use this formula, plug in any endurance value that I want from my video game, and figure out what my maximum health would be. So I'm currently using this to just help my team kind of plan out their armor sets. Anyways, if you want to use this to reverse engineer some of your video game power curves, you can do that. That can eventually let you figure out if there's any diminishing returns. A lot of times in a video game, developers will try to make it so maybe your armor value gives you damage reduction, but you'll never get damage reduction above a set number, 30%. So while it's always increases, it always reaches a limit, right? Approaches the limit of 30%. Eventually, if you get to, we'll say 29%, getting anything above that is only going to give you less than 1% additional damage reduction, and you can use that to try and plan out whether it's better to have more of one stat than another in a video game, and kind of optimize your stats that way. All right, if no one has any questions, I'm going to break there and post the homework to WeChat really quick. So there's 14 multiple choice questions. Because everything is multiple choice, I can't tell you whether your answer is correct or wrong. So you'll have to ask me any general questions if you're going to ask me questions on WeChat. So I'm going to take this up on, this will be Wednesday, I believe, at midnight of next week. Okay, thank you guys so much for coming. If you don't have questions, you're free to go. If you do, feel free to stick around and ask anything you want. Okay, which homework? I'm sorry. Okay.
Yeah, I also have a question about that homework for the first page.
Okay, I'm gonna grab Abby first. So, Abby, which one did you want? Okay, for the box. Okay, so a box plot looks like this. Right. So I'm just asking you what each vertical line. So what does this, and this represent? So I just want you to label this. I didn't give you any numbers here, so I'm looking for general labels. You can do that on a separate sheet of paper if you want. Nope, there's no numbers, so I'm just looking for you to label the box plot. Tell me what each one of these vertical lines represents. No problem. Okay, Nikita, you had a question too?
Yeah, I have a question for the problems from
Goodbye.
for the fourth page, I believe, the one where you have to compare to examinations.
Okay.
Like, I'm not sure how to calculate the probability here.
Give me a guess. What do you think you're doing? It's possible, but you'd need your z-table for it.
Okay, so I think first I gotta find uh, the percentage, maybe.
Okay, percentage.
Wait.
You're right. Percentage of values that would fall between what and what?
That would fall between. That would be less than 65.
Okay, less than 65. So this is the 2018 to 2019 exam. So our mean value is 62.5, and our score here is 65, somewhere out here. If you get this area, that would be the probability that a random test score in 2018 to 2019 would be less than a 65, which is exactly what you're looking for. Okay, so that's it.
Okay.
All right. Anyone else have questions from the homework?
Wait, am I the only one?
Yes.
Oh, like I have a question from like homework. I mean, like the grade now updated like today or yesterday. I think it was about this.
Okay. I'm having a hard time making out what you're saying with all the noise in the background. So, do you have a question on the homework,
Oh,
or?
you know, I'll just like ask it in the chat.
Okay. If you want, you can type it out on Skype, and I might be able to still take you over the video if you want.